Everyone, good morning. Adrian here again, and welcome to my channel, Adrian's Trails. Today we are going to do something fun. Physics. All of you must be wondering, oh no, that boring physics again. But no, we are going to do something special today. Trains and physics. So stay tuned. Please watch till the end. I'm sure you'll enjoy it. Please subscribe and share this video, because I'm sure no one else has done this before.
I'll just explain you the setup. This is a very simple inclined plane setup. I have just fixed a protractor here to measure the angle of the inclined plane, and I've just used a railway book with hardbound covers. So I have perfectly aligned 0 degree with the edge of the book so that when it pivots, I can get an accurate, kind of accurate reading of the angle. You must note that this experiment is just a home setup. It is not accurate, very accurate, but a good approximation. The idea is to give you the fun way of doing physics as well as playing with your models. So the idea is to just give you an approximate angle value at which the model or the rolling stock starts to slide down the inclined plane. I have attached the cathode track to the upper surface of this book, and yeah, this is a very simple setup. And let's begin with the experiment, shall we? So the experiment is to just watch this angle till the time the locomotive on the test track starts to just overcome and roll freely without accelerating. So I move the slope slowly up. So I record a value of around 3 degrees. Let's do it again. So 3 degree gives us the free rolling of this locomotive. Next is this coach, and let's see at which angle this coach starts to roll freely again. Somewhere around 7 degrees. So let's do it again. It's between 6 and 7 degrees. So this gives a value of 7. This is an extreme example. This is a track cleaning coach, so this has a lot of friction. So let's see the angle for this coach. So here comes 15. Yeah, so 15 is the value. So 15 is the value for this track cleaning coach. Last subject, let's try this Roco gondola wagon. Oh, started to move at around 3 degrees. Awesome. It's kind of free rolling. Let's do it again. Yep, so it's 3 degrees. See this Kiro scale coal wagon. The load is pretty heavy here. And let's see how this performs, how the resistance is. So let's start here slowly. It's 5. Whoa, it's pretty good. This is because it has roller bearings fitted. So it has started to roll at less than 5 this time. Yeah. Somewhere around 3 degrees. Super awesome. Most of the wagons that are of good quality, they start to overcome this rolling friction at somewhere around 2 to 3 degrees on an average. So this is following the NMRA railway modeling standards of the resistance friction, the rolling resistance friction. So next step will be calculating this value. On my board I have drawn few formulas. Those of you who were afraid of maths, I believe please stay on. I'll try and make it as easy as possible.
So this is the generic formula for rail modelers to calculate the rolling friction, which is 1000 into tan theta. So in very simple steps, I'll try and explain. So in high school physics, you had studied that for any free rolling object with a slope of theta degrees, we get the rolling resistance friction with mg sine theta, because when the object starts to roll, the left-hand side force equals the right-hand side force. So my rolling resistance friction equals mg sine theta. So for higher the theta value, more is the resistive force. So that's why you can correlate with my experiment. The wagons which had very high resistance, they started to roll down at approximately 10 degrees, whereas most of the other wagons, they started to roll down at around 2 to 3 degrees. Now a small bit of geometry here. Why this formula can be written as tan theta is because for very small angles, we can safely assume sine theta equal to tan theta. This is because when this angle becomes very small, the hypotenuse approximates the base. So h and g becomes the same and they cancel out. So we can safely assume sine theta approximates tan theta. So that's why the rolling resistance which the locomotive needs to overcome on a slope is given by 1000 into tan theta. So for each locomotive, for each wagon, for each coach, we can find the rolling resistance by simply multiplying 1000 into the tan of the theta angle. And the value comes in grams per kg of the coach or the wagon. So for this coach, we get 10 degrees where this coach had begun to roll down the incline. We get an R of 650 grams per kg of this coach. So this is equal to the rolling resistance that the locomotive must overcome if the coach is sitting on a straight line, a flat line. So even if the coach is standing still on a flat line, the locomotive needs to overcome this much amount of rolling resistance. And for most of the standard NMRA certified wagons, we get a theta of 2 degrees, which comes to approximately 35 grams per kg. So provided this wagon is 1 kg of weight, for each 1 kg, you'd be getting a resistive force of 35 grams. But this wagon is hardly, I would say, 50 grams. I'll be making a video on the weight. I'm getting a scale very soon. So for 50 grams, this value is going to be pretty less. So thanks for watching.